Our current model of the universe, the Big Bang, is the best framework we have. But to make the math work, astrophysicists have to rely on invisible concepts like dark energy and cosmic inflation to hold it all together. Recently, data from the James Webb Space Telescope introduced a serious complication. When astronomers looked at a sample of early galaxies, they noticed the vast majority of them were rotating in a single, coordinated direction. Under the standard Big Bang model, the universe is supposed to be random and uniform. If you measure the spin of distant galaxies, you should observe an even 50-50 split between clockwise and counterclockwise rotation. This coordinated rotation suggests the universe itself possesses a preferred axis. It is a significant anomaly, leading researchers toward alternative models that can account for a universe with a built-in spin. If you calculate the total mass and density of our observable universe, you run into a very strange mathematical quirk. Every object with mass has a Schwarzschild radius, the specific size it needs to be compressed down to in order to collapse into a black hole. When you plug the mass of our observable universe into that equation, the physical radius of the universe perfectly matches its Schwarzschild radius. Curious, the immediate problem with this math is that black holes crush matter inward. Everything we can observe shows that our universe is doing the exact opposite. We have a mathematical reality that says we meet the exact criteria for a black hole, and an observational reality showing an expanding cosmos. To reconcile these two conflicting facts, we have to look at the traditional view of black hole formation says that when a massive star exhausts its fuel, it collapses under its own immense gravity into a singularity, an infinitely dense point where physics breaks down. But quantum mechanics introduces a physical limit to that collapse. The quantum exclusion principle, along with a twisting of space-time known as torsion, dictates that matter simply cannot be compressed infinitely. Two particles cannot occupy the exact same space. When the core of that dying star crushes inward, it eventually hits this extreme density limit. Instead of disappearing into a singularity, the matter acts like a tightly compressed spring, halts, and violently rebounds. This massive rebound pushes outward against the intense gravity, carving out a new pocket of space-time that rapidly expands, all while remaining trapped inside the original event horizon. In this framework, the Big Bang is the outward recoil of matter following the collapse of a star in a parent universe, a big bounce that marks the beginning of our internal spacetime. This spacetime diagram models crossing the Schwarzschild radius, the dashed line. Outside, light cones point upward, indicating normal time. But crossing the boundary, the math demands an inversion. Space and time literally swap. To an outside observer, matter falls inward permanently. But if you are an observer inside the event horizon, that 90-degree flip reorients the flow of your proper time. Because time is now moving in the opposite direction relative to the outside, that crushing physical collapse is perceived by you as a rapid, infinite expansion. Our expanding cosmos does not defy black hole physics. Expansion is the exact mathematical reality you experience from the inside when the dimensions of space and time reverse. The big bounce mechanism naturally produces the rapid, uniform expansion we see today. Because this rebound occurs over a finite period before stabilizing, it creates a flat geometry, mathematically fulfilling the requirements of the inflation theory without needing a hypothetical inflaton field. It also provides a physical origin for the JWST rotation anomaly. Black holes form from spinning stars, and the resulting event horizons retain that angular momentum. When a new universe is born inside that rotating black hole, it inherits the spin axis of its parent, giving every galaxy within it a unified, preferred direction. By relying on established gravity and quantum mechanics, this model accounts for multiple cosmological observations using the same set of starting conditions. There are still massive scientific hurdles for this theory to overcome. We don't observe the extreme tidal forces you would expect near a black hole's singularity, and fully proving this model requires a completely unified theory of quantum gravity, which we don't have yet. But if the math holds, it changes what the boundary of our universe actually is. The edge of the observable cosmos is simply an event horizon, viewed from the inside out. And through a process of cosmological natural selection, this implies every black hole we detect in our night sky is doing the exact same thing, birthing new, self-contained universes within their own horizons. This nested model suggests that our reality is just one layer of an infinite, self-reproducing cosmic cycle.